Hi, my name is Vernon, and I'm doing my final Parallel project for, Parallel. And here we go. This is my third time doing it because my audio keeps messing up, and I am sorry. But the numerical method I used is the sieve of Veritasities, and this project is a remake of Assignment 2, where we did it for part 2. I did not get too good of a grade, so I wanted redemption because I really like the sieve of Veritasities. I think it's a very unique mathematical formula. But yeah, so the parallel program methods I used. Oh, wait, sorry. One more thing. The simple sieve has an issue where has a memory allocation issue where it can only go up from, let's say, 1 to 1 billion. Since numbers that big, we run out of RAM space pretty quickly. So so we can only go up that high. But I found another algorithm called the segmented sieve, which is just the regular sieve, but allows you to go from 1 to 64-bit integers, because the way it works is it gets a big number, it splits it up into different limits using a square root of n, as you'll see soon, and then it allocates memory to each segment, goes through the segment, finds the primes, and then frees the primes. And yeah, that's how that works. The parallel programming method I used was OpenMP and MPI and clear. This is how you compile and run my code. So first, let me do make clear. Oh, make clean, my bad. Sorry, I'm losing my mind. Make clear. Oops. Oh, just make. Oh, sorry, I'm losing my mind here. And then you do /OpenC for the OpenMP version 100. You do /segmented, another 100. And for the MPI, you do MPI exec -np, how many processes you want, and then /MPI sieve, and you enter your number. And to make sure it's correct, how many numbers are between or how many primes up to 100? 25. So yes, my code is correct. And alrighty. Now for the code implication, I've done this like 4 times already, so now I'm a beast at this. So so there's 3 different functions in here. There's the simple sieve, the segmented sieve, and the main. The simple sieve just gets the prime list up to the first limit. The segmented sieve gets the rest of the primes. And then the main just gets the input and the timing of it. As you'll see, there's a long int because we're using really big numbers. Also, what you see here, the clock monotonic, there's something wrong with my VS Code. There's nothing actually wrong with the actual code. My VS Code is messed up, but this actually works. As you can see, it runs over here. And so it asks for the user to enter a number they want to go to, like 100. And then it reads in the number. Clock starts the time. And then it passes into here. I use clock get time for the segmented, and for the MPI, I use the MPI W time. But, all right. So what it starts, so these times are for the sequential and parallelization. This gets a sequential right here. This is parallelized, so this gets a parallelized. Another sequential, parallelized. And then this outputs the times. But, so we first start with the limit. The limit is, for each of them, is square root n, or the square root n is the limit for each section. So let's say 100, you go from 1 to 10, or 1 to 11, since there's plus 1. This mallocs memory into a prime list. This will store the primes into that. The primes that finds from number to limit. Then we call simple sieve. First, it assumes every single number we listed in the list is a prime. That's like a perfect world scenario. Let's say we put 2. But then the first and the second number in the list are immediately false because those numbers will be 0 and 1, which are not primes. And then this is the meat and potatoes of the segmented sieve. So the way it works is we start at 2 because we already went to 0 and 1. And then we get that number, we times it by another number as we go up to the limit. And then, yeah, we keep going up. And then this one, we start at this because we already went through the lower numbers. The way this works is every time we times this number to this one, it gets checked off as false because a number times a number equals something. That number that it equals cannot be a prime due to the natures of primes being indivisible. You cannot divide 5. You cannot divide 2. And it goes, so let's say this is, so it goes 2 times 2, which is 4. And then it keeps going up 2 times, this goes 2 times 3, 2 times 4, 2 times 5. Checks and then keeps checking the numbers as false until it hits the limit. And then it goes 3 times the number. And then it just keeps going up and up and up until all those numbers are checked. But the way it works is, so 2 times 2 is 4. 2 is not checked off because we didn't do anything. So 2 is prime. It would go to 3. 3 was not one of the numbers when we multiplied, so it's not checked off, so it's a prime. Then it goes to 4. 4 was found in 2 times 2. It's put as false, and then it gets multiplied, and then we multiply through it. And then, yeah. For the first parallel part, this is just parallelizing the counting of the primes we found in the simple sieve. Each thread is going to have its own numbers to go through. And then we want the addition of all of them together, so we reduce all of them to the prime counts. And then this, we malloc a list of primes by the prime count, because that's the primes we have now. And then we add them to a prime list. This will be used for later. This is where we end the get time for the segmented section. This the meat and potatoes of the program. Excuse me. This so we start from limit plus 1 as our low because we already went to limit with the previous. So we start from the 1 afterwards. And then we go all the way up to n. And every time we go through this for loop once, we add another section, which is another limit. So we started the next limit, which is plus 1. And then the highest is the segment we're in, is the limit plus the limit minus 1. So it's just the lower limit plus the upper limit minus 1. And if our n somehow ends up going above n, it immediately goes back to n because we cannot go past that limit. Then we allocate memory into a mark, which is quote unquote marking all of them. Then, like the segmented sieve, in the segment, all of them get marked as true. So this is where the prime list comes in from earlier. We started the last prime in the prime list. And then we go to a certain multiplication of that prime list, the prime in the prime list, so like 5 or something. So say this like going from 25 to 30. As long as you're below the low, we add 1. And if we're at the prime we're at, we want to go up to another one, which is going to be our next prime. And every single time we find a multiplication, such as the simple sieve, which is our low limit because we had to find a multiplication to get to the low limit, all the way up to high, we mark all those ones as false. And then we get all the ones that aren't marked, as we did in the simple sieve. Then we add it to a count, and then right here, the total primes equals prime count, because we want to start at the top of that list, because we already have some. Then we get number equals number equals number. We just keep adding it to the total primes, and then we free the list we just went through, and then we start all over until we get to n. We time the entire section. This is our parallel section. And then we free the primes list and the number of primes and the primes list at the end of it. And that is the open MPI version. Now the MPI. This code is not up to date, so I will be showing you more on this. But right now, so the simple sieve didn't change. The segmented changed a little bit, but it's the main that we're looking on. So we initialize the MPI since we don't have RGC or RGV. We don't have anything. We just initialize it to null. We don't get any command line arguments. And then the my rank gives an ID to all the ranks in it, all the processes. And the com size is the processes. So then the first rank, aka rank 0, gets the user inputs of n, and then this broadcasts it to every other process or rank. So every single number knows the max number. Then this is the range for each process, which is going to be the max number divided how many processes there are. So the first rank starts at 1, because 1's the first number. Every other rank starts at the rank times the range. So let's say this is 80, because 80 is easy divisible. So this will start at 1, go to 8. This will start at, since that range is already gone through, it will be 2 times 8. So this one will start at 16. And then next one will start at 24, yada, yada, yada. And then this section is calculating the endpoint for each of them. If this is the last rank, then the endpoint is the big number we need. And if it's not that, then it's a chunk between the lowest rank, the lowest local A and the top of it. So this would be 8 plus 8. So this will be 8 to 15 in this scenario. And then this is where I changed the code, so we don't need this anymore. Because originally I used clock time, but I found MPI W time was actually easier when it came to finding doing MPI reduce on, so it just made it simpler. So I could find the segmented and parallel verses. Well, anyways, so let me get rid of this. So we start off with we put a barrier around the time, and then we start the time using W time, and then we send each of the segments to a local int, which holds all the numbers for each segment. And then this is where, so all this is basically the same. The only difference is between these lines. Where, so unlike, that last one where we added all the primes from the segmented sieve into the list. Well, this basically does the same. is basically just saying if the local A is less than or equal to limit, which is the primes we found in the simple sieve, it just adds the primes into the total prime count, and then local A becomes the new limit, or the next limit, which is limit plus 1. So it becomes the new high, or new low. And then this is saying if local A is less than or equal to local B. So this is basically saying if we're past the limit, now we're going to local B. Low becomes local A, and high is basically local B, but since there's segmenting it, it's still low plus limit, so this will be a segment. And then while while local A is less than or equal to local B, essentially, if high is ever greater than local B, aka in the top of the segment, high becomes local B. And then the rest of the code is the same. Yeah. So that is my code presentation. And now for the speed up computation. So for the percent parallel and percent sequential, I actually stupid autocorrect. I actually found that my code is actually really parallel. It is 99.998% parallel to 0.00185% sequential. This is for OpenMP, by the way. Let me use that. So the reason for it is if you look back at the code, every single thing gets done in here except for one thing, which is the first calculation, which is the 1 to the limit. And since, let's say we're using 4 billion in this case, and the square root of 4 billion is like 65,000, and 65,000 is way less than 1% of 4 billion. So our code is very parallelized. So we had a prediction of a two times speed up, 4 times speed up, 8 times speed up, and a 1 time speed up with, one, because 1%. Oh, by the way, with my MPI, I forgot to mention I stuck with one node to make it a bit fairer of a comparison to MPI, or no, OpenMP. And yeah, so just keep that in mind. Anyways, so I got a 1, 2, 4, and 8 times speed up with how parallel my code is. Though I actually so I got a 1 and 1.86 for the 1 and the 2 thread. 1.86 is pretty close to 2. My 4 and 8, I got 2.95 and 2.94. I do not know why the 8 is less than 4, but I think I know why it is so low in the parallelization. It's because our limit is square root n. And square root n is a super small number compared to the big number we're going for. If this was big, which means the parallelization doesn't have much room to work with. If we chose a bigger n, it probably would have been, or a bigger limit, it probably would have been a lot better parallelized. But I didn't really want to mess with it because I didn't know what it was going to do. But compared to my MPI, I got the same parallelization because both of them have very little sequential versus parallel parallelization. Though I did find the MPI to be a bit quicker on the speed up. I did get 1 and 1.86, which is the same for the 1 and 2 on the OpenMP. But for 4 and 8, I got a 3.1 and a 3.07. So in this kind of scenario, MPI is faster than OpenMP. I think it's just because my my MPI code was a little better than my OpenMP code. But if you were trying to do speed up on segmented sieve, I would use MPI. Well, it's at 20 minutes, so thank you so much for listening, and thank you for the semester, and I hope you have a wonderful break. Goodbye.